So, welcome back. We have been looking at reification. Let us continue with that, and we will look at how it turns out to be a useful mechanism when we are dealing with relations which are of arity greater than 2. We have mostly seen binary relations so far, but we may be interested in relations of greater arity. But I will just take a short break, and I want to go back to older video and add a little bit of material to that, and I will be back after that. I think. So, here I am back again. Let us look at our study of relations of arity greater than 2 and see how reification can play an important role there essentially. Now, of course, you can think of many relations. A relation is after all a relation between some elements of the domain. You can have a relation between 2 elements, you can have a relation between 3 elements and so on. And if you are going to be talking about knowledge representation, we have to think about how we will represent these different relations. So, there is a multitude of relations that we can talk of, and how can we handle them effectively. So, in the real world, entities are related to multiple other entities. The question is, how does one capture such relations? This happens in particular when we are talking about events and actions. So, let us consider the use of verbs for describing actions. So, here is an example of an incident about a couple of kids playing and having a fight, and this incident says that Divya hit Atul with a stick yesterday afternoon in the park or in a park. How do we represent this? One might be tempted to simply invent predicate names as and when we come across such sentences. So, you might say, for example, that the predicate is hit and its arguments are Divya. Remember, we are using specific names to distinguish between the various Divyas that might be there in the domain. So, Divya 54 hit Atul 81 with stick 14 yesterday afternoon in park 28. I mean, that is a very lazy way of doing things. The semantics is completely arbitrary, and the user would have to keep track of what parameter represents what essentially. Already we have seen earlier that when we define the son predicate, we have to be clear as to who is the son and who is the parent essentially. So, here the problem would be manifold. And what happens if we wanted to talk of different sentences? Supposing we did not want to mention the park, or we did not want to mention the time and things like that, how do we handle such things? So, let us look at some of these issues now. So, the question is about choosing appropriate predicates essentially. So, if I say Divya hit Atul, I can simply write it as hit Divya Atul essentially. If I say Divya hit Atul with a stick, then maybe I can say Divya hit Divya 54, Atul 81, stick 14. So, I have given 3 parameters instead of 2. Let us assume that we can overload predicate names and that is allowed, but there is a little bit of a problem here. The sentence says a stick, it does not say the stick essentially. How do we handle things like a stick? So, should it be something like what is written here is that there exists an x which is a stick and Divya hit Atul with that x essentially. That could be one way of writing the a stick part essentially. If I said Divya hit Atul yesterday, I would just write it as Divya hit Divya Atul yesterday. So, you can see it is all very arbitrary and ad hoc, and many of the questions that we would want to raise is that how is hit Divya Atul stick yesterday different from hit Divya Atul yesterday stick. The problem is particular to first order logic, because we are formal and we are very precise essentially. Unlike natural languages, in natural languages we have ancillary words which help um, us understand the meaning of the sentence. If you, in particular, if you look at Indian languages, we have explicit case markers. So, you must have studied about karak in your school sometime. So, there are these various cases. So, karta ne, karam ko, karan se ke, dwara, and so on. Those are case markers. They tell you which element plays what role in the sentence. So, who is the actor, who is the object, and so on and so forth. Whereas, when we write sentences like this in first order logic, it is not clear as to what is it that what stands for. How does one know that yesterday is a different kind of thing from stick 14? So, obviously, we should have some information about categories somewhere. How do we know that yesterday stands for time in the first place? And moreover, yesterday is a relative term. When I say yesterday at this point of time, it means the day just before today. But if I were to refer to the same incident after 1 week, then I would have to say something like last week or so on. So, it does not make sense to use relative references. So, it would probably be a good idea to, in the representation, to store the date. And the next question that would arise is, how do we represent a date? So, let us move towards answers for this. The modern trend is to break down complex sentences into binary relations. Everything, all relations you want to store should be a binary relation. So, how do we do that? For example, in this example that we are talking about, Divya and Atul, we could create an abstract type called event and associate everything with that instance of that abstract type essentially, which is an event. So, we could say something like this, that here is a abstract entity that we have created, which is an instance of something which is called a hitting event, which may itself be a type of events, because events can be of many kinds. So, what we are saying in the first line is that E45 is the hitting event that we are talking about. So, we have identified one instance of an event. Then in the second line says that the actor of E45 is Divya essentially. So, you see that we are trying to bring in something which was like case markers. We are trying to make the semantic relations explicit essentially. So, that this is the actor and so on. Then we can state other statements. The object of E45 was Atul. The date of E45 was March 21. The location of E45 was Park 28, and the instrument of E45 was a stick. So, in this manner, what we have done is we have broken down these relationships between many elements, the actor, the object, the instrument, the date, the location, and there could be other things also, and associated each of them with an abstract entity called E45, which is an instance of an event essentially. So, we are moving towards a more systematized way of representing things. And as we will see, this move will help us move towards representing information and knowledge which can be accessed by different programs over the internet. So, notice that we have talked about named properties. So, actor, object, date, location, instrument. We can flexibly choose what we want to talk about. So, maybe we do not want to talk about the date, maybe we do not want to talk about the location. We can choose what to add to the representation. Now, it is also now popular to represent these in a slightly different format, which is as follows. The predicate subject object, which is the binary relation we have talked about. For example, actor event 45 was Divya, can be expressed as a triple. So, it is a collection of 3 items. Some people refer to it as subject, predicate, object. The first element is the subject, the second one is the predicate, and the third one is the object. As you can see, it's the same 3 names that we had used earlier, but in a different order. Subject always comes first. The other way that people talk about is subject, property, value essentially, but both refer to the same kind of thing. And in the triple representation, the same data would be represented as follows. Now, we have triples. I have not used angular brackets, I use normal brackets, but the point is that each of them contains 3 elements. So, the same information that E45 is the instance of hitting event, E45 is the actor, the subject is E45, the property is actor, and the value is Divya. So, we are always going to be talking about the subject, predicate, object, or subject, property, value. The rest follows. E45 object Atul, E45 date March 21, E45 location Park 28, E45 instrument stick 14. The instrument of E45 is the stick. So, we can represent information in this very standardized uniform format. Each triple says something about the subject, which is the first element of the triple. The second element characterizes the property, and the third element is the value of that property. So, nowadays when you represent, so now that we have a well structured representation that everything is a binary relation, everything has 3 constituents, one is the predicate name, one is the subject, and one is the object. We can also now use standardized representations which allow us to store these triples, and these things are called triple stores. Each triple is a binary relation between 2 entities, and we can depict them as an edge in a graph. So, we can even draw graphs to show what we are representing. So, on the left hand side we have subject, property, value, on the right hand side we have subject, predicate, object. Each sentence is stored as an edge between 2 identifiers essentially. So, that is going to be the key, that in the internet we will talk about something called a resource, and everything, an individual and so on, everything would be a resource, and we would link up resources with property edges. So, the subject is a node in the graph, the property is a labeled edge emanating from the subject. The property edge points to a value, and we will see values can be of different kinds. For example, value can be a date, value can be a number, value can be another node which may have its own properties and so on. So, all that kind of complex representation will be possible. They can be stored conveniently in what are known as graph databases, which are different from relational databases, and they have a different query language, and they turn out to be very useful for such representations. So, here is an example of another piece of information that you want to represent, that you may want to represent, and you will notice how we have moved away from arbitrary complex predicates with arbitrary number of parameters or with arbitrary arity towards a standardized triple based representation where everything is like a binary relation. So, this is what we want to represent. It is information about some musical performance. So, these are the facts that we want to talk about. Hadika Kiani sang the Sufi song called Rang on June 10, 2012 in Coke Studio. It was produced by Rohil Hayat and hosted by YouTube. That is something we want to say, and we do not want to say this in one long predicate with many parameters. The second thing we can add now is that this was also sung by Rahat Fateh Ali Khan and Amjad Sabri, and also for the Coke Studio. The song was written by the famous Indian poet Amir Khusro. Another Sufi song written by Khusro is titled Chhap Tilak Sab Chhini. So, I have written only the first 3 words from there. So, how do we represent this in the new format that we are devising essentially? Again, we start with an abstract entity called performance. So, let us call this performance 101 and we will link everything to that essentially. So, just like we said that event 45 was an event and then we related various elements to that, we are doing the same thing here, except that now we have multiple sentences that we are putting in the same graphical representation. So, here we go. We start with this Hadika's performance and there is a relation says that singer is Hadika, the title of the performance is Rang, the genre of Rang is Sufi and Rang is a song. The date of the performance was June 12th, the producer was Rohel Hayat, it was hosted by YouTube and it is in Coke Studio. So, you can see that complex piece of information that we had is now all present in this graph, but as binary relations between elements essentially. So, an edge of course relates 2 of those things. Then the second sentence said that the same song was also sung by 2 other singers also for Coke Studio. So, that is what we can add to that now, that there was a performance 102, the singers were RFAK and Amjad Sabri and this was also in Coke Studio essentially. The third sentence said that the poet of Rang was Amir Khusro and Amir Khusro was an Indian poet essentially, his nationality was Indian. And finally, about the other poem written by Amir Khusro which is called Chhap Tilak Sab, we can add that also to that and also add that it is a Sufi song which he wrote essentially. So, this is the style of representation that we are going to be moving towards and we will see that this way of representing things facilitates a lot of work on the internet. So, much of the things that we traverse, so there are databases on the internet which uses these kind of triple representations or binary representations and we will have a little bit of look at that after this particular video. Even 50 years ago when people had started using knowledge representation, started looking at knowledge representation and started looking at first order logic for knowledge representation and started looking at the way of making inferences, there was already a school of thought which was saying that if you represent your whole knowledge or your whole knowledge base will be a set of sentences and that is what we have been saying so far, then any theorem prover that wants to operate on that knowledge base or want to make inferences on those knowledge base or want to make connections between different entities on that knowledge base will have to search through the entire knowledge base and depending on what is the format, the search would take a certain amount of effort essentially. The other school was thought was, as some people, for example, Charniak and McDermott in their book, they call it concrete representations. By concrete representations, we mean that we have these explicit pointers or links in the knowledge base, which tell you as to for every entity what else is a related item. So, we can just follow the edges to find out what these things represent. Now, that was known as semantic nets or semantic networks and there was a lot of work which we are not going to be talking about here, which spoke about how to exploit the fact that we have these explicit links in the network or pointers in the network and there were these algorithms, for example, marker passing. So, I will just write the name here, you can look it up somewhere. There were these algorithms called marker passing algorithms, which would try to figure out, supposing you have this large network and you have one element here, another element here and you want to say how are they related. You can think of this as an example for your the family database that we had spoken about some time ago. Remember, in the family database, everything was represented in terms of three relations: the parent child relation, the gender relation, that male relation, and the female relation. So, out of which, of course, gender relation was specific to a node, but the parent child relation connected two nodes. It was a binary relation, and everything else was like a path in that semantic network. So, grandfather is your parent's parent, who is a male. Aunt is someone who, at the most fundamental level, who is a child of your mother's or father's parent. So, an aunt is a female child of your parent's parent. So, we are going through some three links. Remember, so if you are here, then your parent is here. So, this is you, this is your parent, this is your grandparent, and the grandparent has a child who is your aunt, and she is a female. This is how we represented. We defined this predicate called aunt essentially. Now, you can see that essentially this is like a path or a certain pattern in the graph database, and the query languages used in graph databases, they are well equipped to recognize such patterns essentially. So, that is in the modern sense, and we will come to that maybe later. But I was talking about marker passing. So, marker passing was algorithm is that if you take two nodes, so let us say Sushma here and Anil there somewhere in the graph, and you want to say how are they related. Then marker passing algorithms would basically search, from both directions and see what is the path between those two these things. And then of course, you can optimize that by choosing the shortest path or the longest path. It will also depend upon whether you have additional edges. So, do you, supposing you have found this definition of aunt, do you may create an additional edge between a person and the person's aunt, because that would make searching faster. So, that again is a trade off between forward chaining and backward chaining. Do you add all the edges that you infer, or do you search the graph whenever the query comes essentially. So, those were interesting issues, and this was more than 50 years ago in this area called semantic networks. Nowadays, people have moved towards something called knowledge graphs. So, a semantic network is a graphical model in which nodes representing concepts are connected with label edges representing relations. The idea of a semantic network has been around for a long time. Some people say even going back to the Greek philosophy time, because remember that even Aristotle was talking about categories and things like that. The Socratic argument that how is the category of men related to the category of mortals. So, people were talking about such representations which connected categories together even in those times. Early work in semantic networks was motivated by natural language processing. We do not have too much time to get into that here. It is often credited to Ross Quinlan, because he wrote one of the papers in 1968, which kind of crystallized this notion of semantic networks and made it more explicit. But the idea had been floating around at that time. Subsequently, the idea of semantic nets evolved into the idea of knowledge graphs, which were semantic networks spread over the internet. So, when the internet came, then you could link different databases together and say this pointer is related to that element in that database and that kind of stuff. And so, we had this idea of knowledge graphs. The idea of the semantic web evolved in this century, a little bit towards the end of the last century. And in 2012, Google adopted formally the name knowledge graph for its representation of its data essentially. So, remember that Google represents crawls the net and represents a lot of data which it uses for answering queries for you. So, here knowledge graph is a proper noun or noun phrase, but we also use the term knowledge graph as a more generic thing, which says that it is a kind of a semantic net spread over the internet, spread over the this thing. So, here is another uh, description of knowledge graph, this time from an IBM site, lest you think that it was only Google which was interested in this concept. There were many people and there was a lot of interesting work going on. This says a knowledge graph, also known as a semantic network, represents a network of real world entities which are objects, events, situations or concepts, and illustrates the relations between them essentially. So, the emphasis is on the network or the semantic network. We call it the semantic network because the edges are named essentially. So, this edge means this relation, that edge means that relation and so on, unlike a graph which has unlabeled edges. The information is usually stored in a graph database and visualized as a graph, and that is how we got the term knowledge graph essentially. A knowledge graph is made up of three main components: nodes, edges and labels. Any object, place or person can be a node. An edge defines a relationship between two nodes. The other phrase that has come about when we talk about the semantic web and so on is the notion of ontologies. Ontologies are basically taxonomies, but they can have other kinds of relations as well. It is an extension of this idea of knowledge graph, in which you have nodes and you have relations between nodes essentially. In the context of ontologies, the World Web Consortium W3C has agreed upon a standardization of the language called OWL, where the acronym is OWL, but the name is Web Ontology Language. It is a little mixed up there. We will look at OWL a little bit in the course next. So, next we will move on to something which I have been talking about on and off, called description logics, how they are represented and how they lead to the construction of ontologies, and how the language OWL plays a role. We may not talk too much about OWL, but we will certainly illustrate how OWL comes into play. All the stuff that makes into what is called as a semantic web. Some people use the term web 3.0. So, we will do that next.